Hi, the next topic is two-sample tests. So suppose that we want to test the hypothesis that mu x minus mu y is equal to d, where d is constant. Then usually that we test if mu x minus mu y is equal to 0. Okay, so the setup is here. So we have the two samples, so group 1 and group 2. And the one sample is x1, x2 up to xn. The other sample is y1 to ym. And we have a sample mean and a sample standard deviation. And our assumption is that x1 to xn are IID normal mu sub x sigma x square. And y1 to ym follows normal, the mu sub y, the sigma y square. So then we want to test this null hypothesis against some alternative. And we have two cases for the two sample tests in 5.3. So one case is sigma x is equal to sigma y. And the other case is the sigma x is not necessarily equal to sigma y. So this is more general case. So both are called the two sample t-tests. And the second one is called the Welch's t-test. And the first one is actually simpler, but it's almost the mathematical formality. So usually the sigma x and the sigma y is unknown because we want to test the difference between mu x and mu y. When we don't know mu x and mu y, how to get sigma x and sigma y. So there are several situations. So the typical situation is that our primary interest is mu x and mu y. So the sigma x and the sigma y are substituted by some different data. So anyway, that's not our primary interest. So we assume that is some constant. Maybe another possibility is that maybe observations come from some machines and the sigma x and the sigma y are determined by the precision of machines, but still we don't know the average, the size or weight of the sample. So we don't know mu x and mu y. So that's still possible. So we discuss this first. Then next we discuss more general case. The sigma x is equal to sigma y. So in this case, basically we estimate only one sigma. So we use both information of x and the information of y to estimate sigma. Okay. So sigma is estimated by the weighted average of the sample variance of x and the sample variance of y. And since the x have more observations, so x has n observations and y has m observations. So we have the corresponding weight. Actually, we lose 1 degree of freedom when we calculate sample variance. So actually we got n-1 and m-1 here. Then the denominator is the summation of n-1 and m-1. Then finally, this is the formula. So this is called the pooled variance, often called pooled variance, since we pool all observations. Okay, so after we estimated sigma by this S, that we can test the difference between the mu x and the mu y. Okay, so here the test statistic. So the most important quantity is difference between x bar and y bar, because we want to know the difference between mu x and mu y. But second important quantity is the variability of x bar and y bar. And actually, if xi follows normal, the mu x sigma square, then the average of x, so the sample mean of x follows normal, mu x and the sigma square over n. And in the same way, y bar follows normal, mu y and sigma square over m. So basically we have to consider the variability of x bar minus y bar. So x bar y minus y bar follows normal, mu x minus mu y, and the summation sigma x, sigma square over n plus sigma square over m. So we have to put this quantity here. I mean, the square root of this. And sigma is not observed, so that we replace sigma by s. Then this distribution, so the distribution of t is t distribution with degrees of freedom n plus m minus 2. So basically, we calculate the to calculate s, we used the x bar and y bar. Okay, so to calculate the s sub x square, we used x bar. So we lose 1 degree of freedom, and y bar the same. So we lose 2 degrees of freedom out of n plus m observations. So degrees of freedom is n plus m minus 2. We don't give an exact proof for this, but just the t distribution, t statistic follows this distribution. So we reject null hypothesis when absolute value of t is large, because you can see that if x bar and y bar are different, much different, then we should reject h naught. So basically t is large, that we reject null hypothesis. So if this is the t distribution with degrees of freedom n plus m minus 2, and we think about a threshold such that the total area of this is alpha. So this is alpha over 2, then threshold is here. So t sub 1 minus alpha over 2 and t sub alpha over 2. But anyway, so this is symmetric around 0. So as long as this test statistics range or this range, we reject null hypothesis to support the alternative that mu x is not equal to mu y. So example. So this is a real data from the Department of Education website in Michigan. So the following data are the average math test scores for 5th graders in 7 Detroit schools and 5 Dearborn schools. So test if the 2 groups have significant difference with a significance level at 5%. So Detroit, we have 7 observations. Minimum is 493 and maximum is 529. The Dearborn, we have 5 observations. Actually, all observations are larger than or equal to the 507.6. So all observations are more than that, and largest is 530. So this is close to the largest one. We want to see how whether or not this difference is significant. So if maybe intuitively, probably that's different because so these observations are all less than 500. And also these are actually smaller than the smallest observation in Dearborn. So considering that situation, probably the Dearborn schools have higher average score. And so this is just sample. So Dearborn have more schools, Detroit have maybe a little less than 100 schools. So this is just a sample from Detroit and another sample from Dearborn. So suppose that this test scores are average score in the building. So that is often distributed as normal. So remember that the sum of many, sum or average the score of many students. If students are identically distributed and independent, then the distribution of the average score is almost normal. So it's good to assume that both observations follow normal distribution. Then, so we define these 2 vectors, the Detroit and the Dearborn, and we can do t-test by t.test function. And we put dt and db. So actually the function itself is the same as the section 5.1, but we have 2 arguments. So first sample and second sample. And to assume sigma x is equal to sigma y, we have to specify this option variance.equal is equal to t or true, true. then you get T statistic. Okay, so we calculate X bar, Y bar, then take difference and the S times 1 over, we have 7 schools, so 1 over 7, 1 over 5, and you calculate S, then this becomes negative 2.07. Okay. So negative 2.07, if you remember a normal distribution, the 95% rule is plus minus 1.96. So 2.07 is larger than 1.96. So almost we reject null hypothesis that the T distribution, but the T distribution has a little heavier tail than normal, so it's not really clear. And this is T distribution with DF10 because 7 plus 5 minus 2 is 10. Okay, then, okay, so negative 2.07. Then what's the p-value for this T statistic? Then the p-value is the area of this plus this. And this total area is equal to 0.0647. So if we use the 5% significance level, actually this is larger than 0.05. So we do not reject null hypothesis at 5% significance level. So the difference is not significant at 5% significance level. So basically, okay, so it looks Dearborn has higher score on average, but anyway, the sample size is very small, so we cannot get strong conclusion. Probably if you want to see the difference, we have to sample more schools.